In this video, we will take a look at Einstein's masterpiece, namely the theory of general relativity, published in 1915. This is essentially a theory about gravity and how gravity is actually not a force, but an effect from the curvature of spacetime itself. As mentioned before, in relativity, space and time unites as spacetime. Thus, we end up with a four-dimensional world with one time dimension and three spatial dimensions. In this video, we will also go through what Einstein called his biggest blunder, which came from a mistake he made when exploring his new theory. The theory of general relativity is ultimately the theory of gravity, superseding Newton's law of gravity, and it is currently the best theory of gravity we have. A core component of Einstein's theory of general relativity is the field equations, which in its simplest form can be written as g mu nu is equal to 8 pi g over c to the fourth times t mu nu. And this might look a bit complicated, so let's break it down. On the right hand side, you have the Einstein tensor, g mu nu. Now don't be confused about the Greek subscripts. They just refer to the fact that this is a tensor equation. And as mentioned in an earlier video, tensors are even more complicated than vectors. So just for simplicity, you can forget about the Greek subscripts. What is important is that the left hand side represents the curvature and the structure of space. On the right hand side, one can see the speed of light c, and again the Newtonian gravitational constant g, which is not the same as the Einstein tensor. Finally, we have the energy momentum tensor T mu nu, and this contains all the matter in the universe. So essentially, this equation has space on the one side and all the stuff on the other side. This equation clearly shows that the curvature g mu nu depends on matter. Thus, when we have a heavy object like stars, they make curves in the spacetime. Likewise, we see that matter is affected by the curvature. Thus, how matter behaves and moves in space depends on the curvature. Thus, these objects have this dynamic effect on each other. Let's take a closer look at the left-hand side with the Einstein tensor. This term can be broken down to two parts. The g mu nu equal to r mu nu minus 1/2 r g mu nu. Here we see three new objects. The first is the rigid tensor r mu nu, which will essentially tell you the curvature of space at any given point. And if it's zero, the spacetime is flat. Notice that a universe without matter does not mean a universe without curvature. If there is no matter, we just get that r mu nu is equal to half r g mu nu. This leads us to the Ricci scalar, which is essentially just a number for each point in space. This number tells you how much the space is deformed. So if you combine this number with the metric g mu nu, it gives you the instructions on how to measure the length correctly in the space. The metric is the fundamental object in general relativity, and it contains information about the structure and the shape of your spacetime. For example, the metric could show a flat universe or some other universe with a weird curvature. If we now move our attention to the right hand side and we take a look at the energy momentum tensor T mu nu, in general it looks quite complicated, and it is a little complicated. First, we note that this object is 4x4, and this is because we're dealing with a four-dimensional space. If we just look at the diagonal, then in the top left corner we have the time component, which contains the energy density, rho. Then moving down the diagonal, we have the pressure in the x, y, and z direction, px, py, and pz. These are spatial components. Then there are the qx, qy, and qz components, and they represent the momentum density, which is a mixture of time and spatial components. Finally, we have tau components, which represent mixing of spatial components, which gives you shear stress. Note that both shear stress and the momentum density components appears twice because the tensor is symmetrical. These four types of components give us the matter-relevant quantities necessary to describe the universe on large scales. Having discussed the components of the Einstein's field equation, one can now consider the full form of the equation, where we have the Einstein tensor capital G mu nu plus lambda small g mu nu is equal to 8 pi g divided by c to the fourth times t mu nu, where we have this additional term with lambda. Now this is the infamous cosmological constant, also known as the dark energy constant. This term is not always included, mainly because for many problems in this field, the effect is irrelevant. The equation is mathematically fine with or without it, and Einstein initially only added it because he was forced to, or at least he thought so. He actually made a calculation mistake which led him to believe that the universe was static. Back then this was also thought to be correct, so he didn't realize the mistake. The problem with the mistake was that without adding this cosmological constant, the math did not allow for any matter, thus he decided to add it. This mistake was later noticed by Russian scientist Alexander Friedman. When Einstein realized this, he removed this cosmological constant again and presumably called it his biggest blunder. But as time would have it, this constant would be added back into the equation to later account for what is now known as dark energy. Now you might ask how Einstein came up with all of this. Basically, this theory just comes from a very educated guess on how the world might look. Einstein used what is known as the two equivalence principles as guidelines for the development of this theory. The first one is called the weak equivalence principle, which was also mentioned in the previous video about Newtonian mechanics. This principle basically states that the inertial mass, as in the Newton's second law, is the same as the gravitational mass as seen in the gravitational force. The second principle is called the strong equivalence principle, and it basically states that locally the physics must reduce to the non-gravitational laws, or in other words, at local points in space, general relativity reduces to special relativity. An important lesson from general relativity is that in this theory gravity is not a force. It is the result of the fact that a free moving particle moves along geodesics. A geodesic can roughly be considered as the shortest curve between 2 points. For example, if you fly in a plane from Europe to North America and you look on a 2D map, then you will see that you're not flying straight but along a curve. Actually, this curve is the shortest path for this route you fly, but since the Earth is 3-dimensional and a map is 2-dimensional, you might think that this curved path is longer. This is similar to the case for geodesics. Thus, the curvature of space makes matter follow these curved paths, and this we perceive as gravity. In this video, we have covered a rather complicated topic, and I hope something will stick and that you learn something. The theory of general relativity can be applied to cosmology, as we will discuss in future videos. Einstein's theory of general relativity is rather complicated. This is also why finding solutions to these equations have taken decades. But today, 100 years later, it stands out as one of the best tested theories. There is, however, a slight issue, and that is that the theory of general relativity is wrong at the end of the day. So, on that note, let's end the video. As always, I hope you like this video. Please feel free to comment, like and subscribe, and stay tuned.